Hey, are you interested in medical electronics, especially in nanomaterials? My name is Wong, one of the current members in Emerging Device and System Group in the Hong Kong University of Science and Technology. Today, this video is about the theoretical study on the cryogenic characteristics of 2DFETs. After watching this video, probably you can gain more physical insights about the carrier transport in 2DFETs. To begin with, let's start with the background of the electronic development. Moore's law is considered the golden rule of electronic industry. It has driven our purchase of making electronic devices smaller, faster, and more powerful. It has been the benchmark for innovations, driving companies and researchers to push the boundaries of what is possible. To meet the requirements, there are lots of process advancements in semiconductor manufacturing. For example, researchers introduced better device structure from planar MOSFETs in the past to FinFETs used in the current process node and GAA architectures in the future technology. Also, researchers also proposed monolithic feed integrations, stacking memory components on the logic devices. Last but not least, researchers also changed the material such as high-K metal gate. Therefore, we can see the researchers keep exploring new materials and architectures to sustain the pace of innovation. When it comes to material exploration, 2D material is one of the candidates to replace silicon as the channel material. 2D semiconductor help expand the transistor scaling with these four major reasons. First of all, 2D semiconductors can be synthesized in an atomic scale. The ultra-thin nature addresses the scaling problem by suppressing the short channel effects. The screening length of 2D materials is short, is very small, which electrostatic control is improved. Secondly, it has a high carrier density, for example, 10 to the power 13 in the centimeter square, and high carrier mobility. These two material properties help boost up the driving current of a transistor. Besides that, they have a suitable bandgap. For example, monolayer MOS2 has a bandgap around 1.8 eV, which is applicable for logic switches in digital circuits. Beyond their remarkable material properties, 2D electronics offer a distinct advantage in terms of fabrication. The transition from traditional silicon-based components to 2D materials is relatively easy. It is because high-quality 2D materials are typically synthesized using CVD instead of epitaxy. Also, 2D fabrication plays nicely with existing silicon processes. It is silicon compatible and can be integrated right into low temperature workflows. It makes 2D electronics suitable for bending of line applications. However, several practical challenges still hidden their development. For example, uniform synthesis, high contact resistance, uniform film deposition. From a scaling perspective, contact problem is the most serious on a single device performance, as the distance from the source to the drain is scaled down. The channel resistance reduced and approaches to the ballistic limits, so electrons travel the channels with minimal scattering. However, contact resistance increases when contact area is scaled down. The high contact resistance results in substantial voltage drops at both drain and source region, which limits the transistor's driving ability. This picture shows the progress made in minimizing the contact resistance of 2DFETs. We can see that at the current stage, through the introduction of semi-metal contact, researchers have successfully minimized the contact resistance and approached the quantum limit. However, there are some abnormal device behavior at cryogenic temperatures. Actually, measuring electronic devices at various temperatures, for example at cryogenic temperature, is common practice, as circuit barrier height is generally extracted through the Arrhenius plot. Different from MOSFET, lowering the temperatures leads to the linear to nonlinear transition in the output characteristics and negative transconductance in the transfer characteristics. This finding suggests that unusual transport behavior may be caused by the contact interface in 2DFETs, which is still not well studied. Therefore, there are three major research objectives of my work. First of all, it aims to uncover the underlying mechanisms that contribute to this output characteristic and transfer characteristic at cryogenic temperatures. Secondly, an empirical model is derived to relate the onset voltage and the temperatures and the contact metal work function. Last but not least, circuit level simulations are performed at different operating temperatures to predict how the temperature influences the performance of 2D circuits. To begin with, it is important to recognize that the contact resistance in 2DFETs comes from the metal semiconductor junctions. In most cases, it refers to the source regions because it is the place where carriers come from. To achieve a high carrier current flows, it is essential to form a metal semiconductor junctions that avoid rectifying behaviors. Therefore, we start with the physics at metal semiconductor interface. In most of the 2DFETs, the metal work function is typically higher than the semiconductor Fermi level due to the Fermi level pinning. No matter what traditional metal electrodes are used, there are a small barrier height from 50 mV to 200 mV. Therefore, the metal semiconductor junctions form in this shape. If a positive voltage is applied, the forward current can be derived using the fermionic emission principle because the electron flows from the semiconductor side to the metal side. The equation of the forward current can be derived in this way. But under the reverse bias voltage, Fn tunneling is the mechanism responsible for the current flows in the metal semiconductor junction. When reverse bias is applied, the energy bands of the semiconductor side bend down, cause the depletion width to be thinner. Despite the presence of the potential barrier, the electron from the metal side tunnels through the barriers and moves to the semiconductor side. The reverse current is expressed in the following equation. Therefore, to minimize the contact resistance and achieve the ohmic behavior, it is essential to optimize both the fermionic emissions and the tunneling transport by minimizing the barrier height and narrowing the depletion width. After going through the physics in the contact region of the 2DFETs, we go deeper to the operating mechanism of the 2DFETs by adding the gate terminal. Unlike the conventional MOSFET, where current flows in the inversion regions, current in junctionless transistor flows in the accumulation regions. Consider an N-type semiconductors with a low circuit barrier height, for example MOS2 with low metal work function contact. Under positive VGS, the accumulation of electrons forms a conductive path for current flows. On the other side, When negative VGS is applied, the inversion layers create a large barrier that blocks the electron flows. As a result, we get the off state. But to quantitatively find the dependencies of the electron densities on the gauge voltage, we have to use the energy conservation equations to get the first equations. We can rewrite the expression by defining these three boundary conditions. Since the electron density in the semiconductor is related to the position of the quasi-Fermi level, we get the second equation like this. Then, the dependencies of the current densities on the gauge voltage can be derived by combining these two equations. Although the final equation looks complicated, here is the takeaway. When the VGS is smaller than the threshold voltage, the carrier density is exponentially proportional to the gate voltage. And on the other side, when the gate voltage is larger than the threshold voltage, the carrier density actually is linearly dependent to the gate voltage. With the understanding of the gate modulation, the IV characteristics of the 2DFETs with ohmic contacts at both source and drain region can be examined. Given that the current remains consistent for every S, we can rewrite the equation ID over W by substituting the derivative of Vh, which is come from the previous slides. After doing some mathematical calculations and variable definitions, we can derive the current expressions in terms of carrier densities. Then, by setting different kinds of boundary conditions, actually, we can see that the derived equations are actually the same as the conventional MOSFET from subthreshold region, linear regions, and saturation region. However, this kind of calculation still cannot explain the temperature effects on the IV characteristics of a 2DFETs. MOSFET and 2DFETs look similar, but they are two different devices. For example, carrier density and the contact interface. Probably we missed something or set a wrong assumption in the previous derivations. Therefore, we guess the problem comes from the contact because the gate modulation on the channel band bending is the same, while the contact mechanism is different. To experimentally validate the ohmic to non-ohmic transition, 2DFETs is fabricated with the cross-sections as shown in these figures, while the device parameters are listed in the right side. We intentionally picked nickel as the contact electrodes to match the reported data and to achieve the ohmic contacts at room temperature. When we measure the fabricated device with different temperatures, we observe four different behavior: SS reduction, V-tip shift, increased on current, and the non-ohmic transition. To study the mechanisms behind the transitions, we investigate the temperature effects on the contact part. The contact interface between the metal and the semiconductor film with MOS2 material properties is analyzed using the Savago TCAD simulations. In order to match the experimental conditions, the metal to semiconductor barriers is intentionally selected 100 millieV. At room temperature, the simulator displays the linear output characteristics, which is consistent with the previous slides, which is the experimental data. When the temperature is reduced, the reverse current remains the same, while the forward current is reduced together with the reduction of the temperatures. To explain the observation, we analyzed the conduction band energy of the metal semiconductor contact at different temperatures under the reverse bias conditions and forward bias conditions. First, let's start with the reverse bias conditions at low temperatures. At low temperatures, the barrier height from the metal to semiconductor increases slightly, while the conduction band of the semiconductor moves closer to the Fermi level. Figures in the right-hand side also illustrate that the carrier conduction under the reverse bias is mainly due to the tunneling and remains unaffected by the temperature change. Also, the increased barrier height is offset by the narrowing of the tunneling barriers, which is cancelling the effects of each other. Therefore, we can say that the reverse current remains unaffected by the temperatures. In the forward bias, the current at room temperature or high voltage bias is mainly driven by drift due to the E field at the junction forcing the electron to move from the semiconductor side to the metal side. However, at room temperature, we can say that the forward current mechanism becomes diffusion because the band bending moves closer to the Fermi levels, results in the built-in potential in the metal semiconductor junctions. Therefore, the built-in potential blocks the carrier flows and results in the reduced current at the low voltage condition. The switch in the conduction mechanism can be more easily seen when we plot the low bias regions of IV characteristic in a log scale. We clearly observed that the two different conduction mechanisms of which diffusion dominates as the low bias regions, while the drift mechanism plays off as a higher bias condition. The diffusion current decreases with the reduced temperature due to the higher potential barriers and lower thermal energy, so that the numbers of electrons able to overcome the barriers also reduce. Following the examination of the temperature effects on the metal semiconductor interface, we simulate the 2DFET with this structure. To maintain the simplicity of the analysis, some of the secondary effects such as interface states may be ignored in this level. To explain the impact of the carrier motion at different temperatures, the conduction band of a 2DFET at low drain voltage is plotted. In this graph, the gate voltage is adjusted to maintain the same VG minus VT for all curves to cancel out the temperature effects. It is observed that under small voltage, the source-to-body condition is not affected by the temperature change, while the barriers for the electron movement from the channel to the drain increased. Therefore, under low drain voltage conditions, the carrier condition is not only limited by the source-to-body carrier injections, but also limited by the channel-to-drain conduction. To overcome the increased channel-to-drain potential barrier, a higher drain voltage has to be applied. The simulated effects of drain voltage on the channel-to-drain barrier's height is shown. We can see that although the electron overcomes the source side barriers, which is here, and injected through the tunneling. Only a number of carriers can further diffuse to the drain side because of the presence of the barrier. Based on the new understanding of the carrier conduction mechanisms, we simulate the IV characteristic of the 2DFETs. Here, we assume that the 2DFETs is fully turned on, so that the channel resistance is relatively small. Under this assumption, the channel behaves as a resistor, which the resistance reduced as the temperature is lowered. As shown in this graph, the simulated IV characteristic shows the linear to nonlinear transition, aligning well with the experimental results. Also, by linear extrapolations, the onset of the turn-ons is shown in the bottom figures here, indicating a good match between the simulations results and the experimental data. Notably, the turn-on voltage can be effectively reduced by minimizing the socket barrier height. Not only the drain voltage, the characteristic of 2DFET is also depends on the gate voltage. When the gate voltage is fixed as the low bias, the current at different drain voltage is shown in the previous slides, which we believe that the non-linearity is due to the drain barrier. This is observed that at low drain voltage, increasing the gate voltage initially improved the linearity of the output characteristics, but eventually results in sublinear behavior again. This behavior can be attributed to the formation of higher channel to drain barrier due to a higher gate voltage. To quantify the effects of gate bias on the drain contact-induced nonlinearity, we simulated the transfer characteristics of a 2DFET with varying VDS from 80 mV to 120 eV. The bottom figure shows the transconductance extracted from the top simulated transfer curves. As seen in the transfer graphs, the simulated device displays a negative transconductance behavior at very high VGS and very low temperatures. With increasing VGS, the formation of drain barrier prohibits the drift of the channels to drain sides, reducing the currents and leading to the negative transconductance. To overcome the drain barrier, similarly, a higher drain voltage has to be applied. With increasing drain voltage, the negative transconductance behavior is less obvious since the high drain voltage effectively eliminates the drain barrier. When drain voltage is sufficiently high, it creates a strong E field to bend down the conduction bands that reduce the potential barriers between the channel and the drain, allowing electrons to flow freely to the drain side. When using the device for electrode circuits at cryogenic temperatures, the value of the onset voltage plays a key factor to determine the operation point where the transistor begins to conduct. The delay of turn on occurs only when the applied voltage is sufficiently small. The onset voltage exhibits a complex dependency on temperature and socket barriers. To derive an accurate model, we employed a systematic empirical approach. Extensive device simulations were performed across practical range. For example, temperature from 110 K to 300 K, socket barrier height from millidegree to 150 degree, with onset voltage value extracted through the output characteristics. Using the Gaussian curve fitting, the onset voltage equation can be expressed as below, with the ABC empirical fitting parameter. To fully understand the impact of this device-level degradation, we analyze the effect on the fundamental circuit block, which is the inverter. An inverter is a basic building block in the digital circuit, consisting of two transistors, one pull-up transistor and one pull-down transistor. The inverter is simulated through the Sparkle TCAD by connecting both PFET and MFET devices. The structure of the PFET is identical with the MFET, and the device parameter of PFET, for example, VT, onset voltage, on current, are adjusted to match those in MFET. Figures here shows the voltage transfer characteristics of the simulated inverter. At room temperature, the VTC exhibits a clear switching point with a deep transition from high to low output nodes as the input voltage increases. At cryogenic temperature, some improvements can be observed. The VTC at cryogenic temperature exhibits a smaller high to low transition zone, benefit from the vessel voltage shift, which reduce the noise margins and increase the gain. However, the reduced voltage range degrades its performance. The decrease in the high-level output voltage and the increase in low-level output voltage are mainly due to the sublinearity effect in the transistor. The sublinearity region, the transistor exhibits higher resistance under small VDS, while in active mode, the increased resistance restricted the current flows, resulting in the diminished ability to pull the output node to the desired level. When scaling down the VDD, smaller voltage ranges are expected as VOH decreases and the VOL increases, which introduce more errors in signal processing. In conclusion, in this work, I explained the performance degradations of 2DFETs at cryogenic temperatures by presenting the concept of channel-to-drain barrier. Furthermore, experimental findings from a fabricated field layers MOS2 transistor and TCAD simulations are employed to illustrate the cryogenic degradations and analyze the underlying physics. Furthermore, gating effects on the drain barriers, onset voltage model, and circuit level degradation are also analyzed. Regarding the future works, in terms of parameter extraction, it is a good way to extract the parameters through the TLM structure and the 4PP methods to analyze the cryogenic results deeper. In terms of the circuit's perspective, standard cells such as inverter, 60S-RAM, and NAND cell can be fabricated using suitable metal electrodes and measured under cryogenic conditions for the CMOS applications. In terms of device simulation, frequency response should be conducted to extend the discussion in this work, as carrier transport is also affected by the frequency. This is the end of my presentation. Thank you.